Hi, I wanted to discuss what the Smart Doorbell project was about. Basically, the aim was to make use of this Texas Instruments CC2640R2 launchpad board, which has got a chip on it, which has got a microcontroller on board, ARM Cortex M3, I think, and also, as well as that, it's got Bluetooth capability as well. To make use of that, to construct a wireless doorbell system, which has got more features than existing systems out there, like, for example, better range or longer battery life. Also wanted it to be portable so that you could disconnect the chime module from the DC mains adapter and take it outdoors, for example, if you're working in the garden. And wanted it to be loud, have high quality sounds, and also wanted it to be compatible with other systems as well that use Bluetooth LE. For example, I wanted to have some extra features when this was combined with the Pi or BeagleBone Black, and I discussed that in some detail later on as well. Okay, so I had 10 weeks to work on this, but actually I spent about 8 weeks on this, evenings and weekends, and 2 weeks in Florida. So I was new to this chip, but it wasn't too bad or too difficult to make use of it. The development environment is called Code Composer Studio, which if you get used to it, then every Texas Instruments chip, microcontroller chip, makes use of that. And it's running an operating system on board as well. This is very like Linux in terms of the APIs that are available, very POSIX-like actually. And there's sample code as well. One important thing which I needed but was not really available completely, I had to make some fairly substantial code modifications, was the audio code. That wasn't quite ready, so I had to adapt it to make it work, because obviously for a chime module for a doorbell, it's very important to have audio. And for the audio, I was using the digital interface. So it's the digital interface called I2S. Sorry, not I2C, I2S, and it uses three or four lines to communicate to a sound card. And I used this sound card here. It's a homemade one, which I developed for another project. It's got an amplifier on there, and it's got connections that you can hook up to headphones or a speaker. So for the initial testing, I actually use this just connected up to the launchpad board. If you don't have one, then there's plenty of ready-made ones out there, like the Pi's got lots of audio cards, and you could rewire it and connect that up to here as well, because it's all compatible. It's a standard. The standard uses like a bit clock, runs at a high speed, and also a left-right audio synchronization type clock, as well as the audio, which is another serial line, and that carries signed integer data, which can be 16 or 24-bit, for example, depending on what quality audio you want. I use 16-bit for this project. Parts 4 and 8 of the blog posts, I created 10 blog posts, so parts 4 and 8 cover I2S, and also they cover sound synthesis and FM synthesis as well. I researched FM synthesis a while back and studied some engineering papers, and also looked at the Yamaha DX7. And that's got 6 operators, which are oscillators, which you can combine to make all sorts of interesting sounds. And I developed some code. I wrote it in C so that it could be portable to many different microcontrollers. And it's a 4-operator polyphonic capable. So it's not quite the same level as a DX7, but it can make interesting sounds as well. And the reason for doing that was it doesn't waste much RAM, because FM synthesis was developed at a time when there really wasn't that much resources on microcontrollers. And so it's actually, really perfect for microcontroller use. The code is very proof of concept at the moment, but it does function. So for the circuits, what I wanted to do was actually use 2 of these modules, and use one of them as the bell push one, and use the other one for the chimes. And the code, the circuits for them are in blog posts 5 and 6. And really it's quite simple, because what I did was, for the bell push, all I did was just hook up a temporary button just to test it. Quite easy. And obviously for the chime module, as mentioned, that had the sound card connected to it. So I could do some basic testing while I was waiting for the circuits to be completed. And the circuits that needed to be made, one was the audio functionality. So that was this board here, and it plugs on top of the launchpad board to provide all of that capability. And if I quickly walk through this, power supply 7 to 12 volts, I think, gets connected to here. It gets dropped down to 5 volts, which powers the audio amplifier here. Also, that power runs to two 3.3 volt DC linear regulators, and these power the audio chip. So the digital power and the analog power is separated here, and then the audio output from this digital analog converter goes out. It's filtered here, and then it goes across to the audio amplifier and out to the speaker. And the digital lines, the I2S lines, are the three of those lines are plumbed here to these connections over here. And there's a couple of buttons and a for volume and LED for indication as well. And also from here, the 5 volts, the DC in from here goes to a constant current source here, which creates 5.8 milliamps, I think, which goes out via these connectors here to the rechargeable battery, and it basically does trickle charging, and that can be switched off as well. So if it's being used for very extended periods plugged into the DC supply here, then it will switch off the power, the trickle charging power to the battery to preserve that. Here's a bell push module. I built several of these, but I only had enough parts to fully complete 2 of them. And let me get that in focus. Really on here, all there is pretty much the CC2640 chip. Here there's an antenna here, which is based on the design on the launch pad. So it's intended for operating in this orientation actually. This should provide good coverage in a donut kind of shape in this direction here. The other things on here, there's a micro switch which is used as a doorbell push thing. So when this is inside an enclosure, wherever the button is, a lever will activate this. And there's an LED again on here. There's also an expansion port which is used for connecting another board. You could sandwich another board on top with springy contacts that connect to here, and that could be useful if you wanted to connect some sensors up, like measure the temperature outdoors, or actually wire up more buttons on another PCB for maybe an apartment block or something. So there's lots of flexibility. There's some serial interfaces on here, a UART as well. And on the other side, there's the clips for the battery. So it just uses an AA size battery, but a lithium one, 3.6 volt. That just clips in here. There's a button here for pairing. And also there's this thing here, which is just some pads for the tag connect header. So this is a difference between this board and the larger launchpad board, because this has got a built-in debugger right here, which has got a USB connection to the PC, and when you're running Code Composer Studio, then that will allow you to program the board up without needing any extra hardware. But this board is much smaller, so I didn't have space for that. So what I do is I use this thing. It's got some springy contacts on there, so when this gets pushed against this in the right orientation, the contacts touch here, so you just hold this pressed while running the programming instruction using Code Composer Studio, and within about 10 seconds it programs up the board. And the nice thing is this external programmer, it looks exactly the same to Code Composer Studio as does the Launchpad, so you don't actually have a different workflow or anything when you're using this. The only other thing was this did not have the right connection out to here, so I needed some interface board, and I built that. So the circuits, the CAD files for this are in one of the blog posts. So if you want one of these, then it's quite easy to actually send this out to get made. Okay. So I had the boards, and the next thing was to figure out how to do the coding as well. And blog post number 9 contains lots of information on Bluetooth LE, how it works, and also how to make use of it using software. And there's about 4 ways that BLE can operate. It operates either in a broadcaster observer or a central device or a peripheral device. And broadcast is something that doesn't need to receive anything, it just sends information out. And an example of that could be Bluetooth beacon, which is used for maybe location-based services, kind of like indoor GPS. There's also this module here. This is a Silicon Labs sensor pack. Sorry, let me get it focused. called a Silicon Labs sensor pack, and it's got lots of sensors on here like heart rate monitor, motion and temperature and things like that. And this operates in that broadcasting mode where it just sends out advertisements, and so any device can connect to it. You could actually have several of these and then scan and collect information from all of them. And the device that's doing the scanning and just receiving information but not actually not transmitting any information out, that's called the observer mode. So broadcaster and observer go together hand in hand. But if you want to do bidirectional transfer of information, then you need to use the central and peripheral modes. And that's what I decided to use because I figured at some stages I might want to send information back to the bell push button to provide some indications to the person who pressed it, whether someone's actually coming to the door or not. Or there could be many other reasons for transferring information back and forth. And if you want to do that, then the device that's sending the information out, that's called so in this case, a bell push button, that's called the central mode of operation. And the chime module will then be operating in the peripheral mode. And another cool thing then you can do is, because Bluetooth LE is standard based, you don't have to use this hardware and you don't have to make code changes to add to the system. So what I did was I took the Pi and made that run as in peripheral mode. So this central mode device communicates. So if somebody pressed a button on here, it would communicate to the peripheral mode Raspberry Pi, and then you could send the information from here over the internet to another Pi. Don't have one here, but I've got BeagleBone Black, same thing. So I can send the information over the internet to this device, and then this can operate in the central mode and talk to the final peripheral mode. Everything's falling apart, to the peripheral mode chime module. So you can see that I can then extend the reach all the way from one location, communicating from here to here using Bluetooth, and then over the internet to the other device, and then from here to here using Bluetooth as well, Bluetooth LE, sorry. And this works. So the code for doing that, or any general application where you need the peripheral and central modes running on Linux-based systems like the Pi, that code is in blog post 9 as well. Okay. So I suppose I should move on to the demo of the system. To do that, I'm going to connect this to the launchpad board to finish the construction of the chime module, and also connect a battery to it. I've got a rechargeable battery here. So the idea is that this particular connector is kind of like the connector used on LED lighting. You can use a screwdriver to push down here and just shove these wires in there. So you don't actually need to wire up a connector to the battery, which is great. So once that's connected here, and once this is this way around, once this is sandwiched onto the launchpad board, then this battery, using double-sided foam tape, I can attach that to the back of here. It should all be quite compact. And just for testing, to hold everything together, I just took a piece of plastic and just put some spacers there. You've got to be careful to use plastic spacers near the antenna, because otherwise it's going to affect the performance of it. So you need plastic screws and plastic spacers. One other thing that's important is when you do this, the board here normally gets powered off the USB here, but when you're using the power from an external board, then you need to be careful about moving some jumpers. So normally the jumpers are in this configuration, and the 3.3 volt jumper here, it's marked 3.3 volts here, that needs to be disconnected. You can just leave it hanging off one of the pins, for example, like that. So that's now disconnected. And the other thing is here there's a power source connector, which is normally, there's 3 pins and it's connected to the top 2 pins. That needs to be moved down as well to the bottom 2 pins. And that's it. Now you can plug on any other board on here and supply power to the 3.3 volts and ground connections on here, and that should power this board as well. Okay, so here's the finished chime module, and so I mean, this is just for demo purposes. Obviously it would be in a real enclosure at some stage, and like I mentioned, the battery's under there and that's connected to this top board. and then power supplied to the launchpad board from here. And the only other thing is I've not connected the speaker up because it's really loud. So for this test, I'm just going to be using a much smaller speaker rather than that one. And that can be plugged in here. There. And I also, it was playing a tune, but I've set it to do a chime type effect for now because the tune was really long. And so if you want to hear that, then the code for that is available as well on one of the blog posts. I can't remember which one. And you can run that on any platform if you're curious. Okay, I've done some current measurements as well. And when it's running off the battery, then it's taking about 8 milliamps of current consumption when the chime's not on, and that means the battery should last a really long time because it's a 600 milliamp hour battery in there. And okay, I can plug this in. So now it's running off DC power, external power, and it's also charging the battery as well. And here's a the bell push module. For that, I don't have an enclosure yet, so I'll just plug this in. Hopefully get the battery the right way around. So now this is running, and it's consuming about 45 microamps. And I think I can get this down to 20 microamps with a code change because I had a look at the datasheet. And but even with 45 microamps, this is going to run with this battery for about 4 years. This is a 2.6 amp hour battery. But I do want to change the code to get it down to about 20 microamps, and then this should last virtually the shelf life of the battery. But even 4 years is pretty good, I think. And when you press the button, then on average it takes about 12-13 milliamps while it's communicating with the chime module, and then it goes back to the 45 microamps. Okay. So if I just move that so you can see the light on there as well. So if I press the button on here now, it should obviously make a chime. It takes about just under a second for the communication to work because obviously it's collecting characteristic information. There's more information on that in the blog post, but it does some exchange in terms of it collects characteristic information, and then it sends the instruction on which chime noise to make. And that all takes just under a second, which I thought was fine because many other wireless bell systems take about that much time as well. But I think I can reduce it further by just not collecting so much characteristic information, because I was using some demo code and just adapted it. So the code does need some rework, but it is functional. It does run. And also the other way I might be able to reduce the time is obviously remove the advertising, because that's not necessary if I've paired this. Okay, so this is running the code, and so now if I press the button, it should work. I'm just going to move here so you can see the light on there as well. So, and from the light flashing, you'll be able to also figure out roughly how long it takes as well from the button press. So if I press the button now, so about a second, I think, or maybe just slightly less, which I think is fine. If I press that again. The other thing is, if I then unplug this, so at the moment it's charging the battery, and if I disconnect that, it's now running off the battery power using about 8 milliamps, so it should run for still a really long time, and it should still carry on working as well. So if I press the button here, yeah. Thanks for watching.